first of all, let me go back to whatever. As usual, I'm not sure it should be as usual. I need to make a correction, but you guys already know that. I don't know. Okay, that's one more. So, let's see, where are we? Oh, yeah, I need to make a correction. Like, as one of you guys pointed out, that like, okay, yes?
Let's go try.
Okay. Testing? Oh, okay. So, okay, I made a mistake when I talk about like the Jacobian stuff. Like the Jacobian, the size should be like just have a dimension like input multiplied by output. So, therefore, like for the example, that what we talked about last time, this guy here, if I just look at this operation, so number of inputs is 6 and number of output is 2. So because W multiplied by X, I get Y, just 2 dimensions, right? So the size of the Jacobian will be just 12. So I made a mistake there, like saying something like, okay, I forgot what I said, but I definitely said something wrong. And so, but the point I want to point out here is like, okay, if you implement this thing naively, so you try to, in the forward pass, you compute the output and also like compute the local partial derivative for the output with respect to each of the inputs, right? That will be like 12 different values. That will store basically the whole Jacobian will be stored here. But know that like if we actually try to exactly compute what is the partial derivative of the output with respect to the input, then we know that like for example, when we compute the partial derivative with respect to Wij, the values will be just like this thing, right? Wj. So what I mean is like, you only need to store 2 values and you will able to recover all these 4 derivatives, right? So even though there's actually not 4, there's 8 of them. Oh, sorry, I want to make sure. Yeah, 8 of them, right? Because I can have like k is basically like 1 and 2, and ij, each of them can be 1 and 2, right? In total, that should be like 8 values here. But if I know the formula ahead, and depends on how I implement that, I only need to store 2 values, right? I only need to store like x1 and x2, and I will save like quite a lot of space there. I mean, in terms of memory. And in terms of partial derivative of x, it is similar also. So actually not exactly. We cannot store that, save that much for the partial derivative of x. Then originally there should be 4 values if we do it blindly, and even we don't do it blindly, there's still 4 values there to store. In this case, for the partial derivative of this guy, we can't save anything. But for this guy, we just do a little bit. I mean, if we know the kind of what we are doing, then we can actually save quite a lot of space. More precisely, we can save from originally 8 of them to just 2 of them. So in total, I need to 12 store like 12 different values here, right? But I can go down to just 6 of them. So I can cut them down by half. Okay, that's the first correction I like to make. And I want to repeat a little bit about merging gradient also. I guess I didn't articulate well here. So when you have like one input, and having like one computational node that have like multiple outputs, essentially what you can kind of like interpret this as just simply, let's say I have x and have y1, y2, and have an f function here, let's say, and I may have like these 2 actually have different output, right? I have maybe 2, this one is f1, y1 is equal to f1s.
Here are some results from the web.
Okay, definitely not some result. I should, maybe okay, so, and I will have y2 is equal to, f2x, let's say. And then like, I can just redraw this computational graph as basically I have x here, and my bench out here have two different nodes, right? One is like f1 and one is f2. One output is y1 and one output is y2, and so on and so forth. Continue to go forward onward until I have some values, like some loss function, let's say. And remember, when we're going back to compute the derivative, what we are computing is just the derivative of L with respect to each of the variable here. So, and therefore by chain rule, we have like partial derivative of L with respect to x is equal to L with respect to y1 given x plus L y2 partial y2 given x. So then you can immediately see that we are just, and this is basically when you compute the backpropagation of the derivative here, right? So when you backprop this guy up to here, you have this term, right? And when you backprop this guy from here to here, you have this term, right? So therefore, it's just simply adding the partial derivative for L with respect to x, just adding these two terms together. So that's, I guess, I didn't articulate well last time, so I just want to kind of comment it. So that's basically all the correction I like to make. And more guys coming in now, so let me start with the topics we want to talk about today. Let's see, we go back to, we end somewhere when we talk about implementation. Afterwards, some remark on BP, maybe just as a review for people that who came in late. So again, like the whole point that what we are compute, the whole whatever we're trying to compute is really just let's get to one of these example here. So we want to construct a computational graph. We have certain function at the end. Sometimes it's the loss function, and the input here can be like, here I have W0 and X0, something like, you can think of like W0 are the weights, or like you can have maybe the others are the weights, it doesn't matter. But the point is I want to compute the partial derivative of this final output with respect to each of these variables. But to compute this efficiently, we need to go step by step. We essentially, on the way, we'll compute all the partial derivatives of L with respect to all the intermediate step. And what we did, as we discussed last time, is simply we backprop the partial derivative each time multiplied with the local derivative on the way. And that's the backpropagation algorithm. So if we go forward one time, when we go forward, again, we'll compute the output and also compute the partial derivative, local partial derivative of the output of each node with respect to input of each node. And you can store this partial derivative just linearly, or as I mentioned just now, that like for some computational node, maybe it's more efficient that you store some other values rather than all the partial derivative like directly. For example, the example I just gave again, for this guy here, if I kind of like, there's 2 outputs here, 4 inputs here, therefore in total there's supposed to be like 8 partial derivatives, right? So if I compute all 8 of them and store 8 of them, so I need to store 8 values, right? But if you just go through the algebra, the partial derivatives for each of these output with respect to these inputs will only be given by this guy, right? And that's basically just 2 possible terms here, right? And we can draw from this x1 and x2. So therefore, in this case, if we kind of do it a little bit intelligently, or or I shouldn't say that, or like you're willing to put more effort into that, then you can save your space from storing 8 values into just saving 2 values. Okay, so okay, that's BP. And again, like BP is just compute the derivative, then we need to talk about optimization still. We haven't. Maybe today or tomorrow. Not tomorrow, next time. So today we will talk about other aspects of a neural network. First, we'll start with the activation functions. So, if you remember, like, of course, like the computer, essentially, like the picture we have earlier is more general, right? We have each of the node there is some kind of computation nodes and take all inputs and do some computation and get some output. But if we go back to a little bit more, I would say a classical neural network or a important computational unit for the neural network, it would be like you do some simple addition for all the inputs, and afterward you go for an activation function. And for this activation function, if it's just a step function, then it will this combination here will simply be a node for a perceptron. And we can have other activation function also, right? We mentioned that maybe we can have a sigmoid function, and we can have like 10H, like a ReLU, and when we look into each of these here. And so okay, sigmoid probably is the one of the earliest one after the step function, because it is very much kind of you cannot do a analogy with the biological neurons, right? You're thinking, okay, it's a neuron, it's either firing or not firing, and here it's very similar to a step function that, like, okay, if you're bigger than a certain threshold, then you will fire. If you're less than some threshold, you'll be fired, and you will not fire. So here we just like smooth the step function a little bit, so that, like, because after we smoothing that, then the whole function is continuous and also like have derivative are all defined, then you can do the backpropagation. So yeah, this is the earliest one, but there's some kind of cons for this this choice of activation function. First of all, like this saturation region is actually not too nice. Because if you think of that, this saturation region is essentially the derivative is equal to 0. The local derivative is equal to 0. So you have say you have some inputs coming in, you go for this sigmoid function here, and when you backpop the derivative, remember that, like, it will be simply this backpropagated derivative multiplied by this local derivative, right? So therefore, like, if you are at the saturated region, something like here, you multiply essentially to 0. So therefore, like, no kind of like derivative information like can be going back from here. I'm going through this node here. So that's also one reason why, like, if you use formulation like that in the past, you cannot go very deep. If you have a network pretty large, then essentially, like, you will have some of the nodes will get to the saturated region, right? Then basically your derivative, when you will try to backpropagate it back, it will just, you will just eventually get the derivative become all zeros. So if your derivative is 0, then it just means that, like, you can never learn, right? Because you rely on the derivative to vary your to train your model, or basically you just find the optimum, right? You're just going down the gradient, right? Essentially, if your gradient is 0, then you just cannot change your variable at all, change your parameter at all. So, and another problem here, let's see, where am I? Yeah, this is, and another problem here is that, the sigmoid function is not centered in 0, or like the output is not centered in 0, or like it doesn't have a 0 mean. So one disadvantage for that, or actually more precisely I should say, like the output of this activation function is always positive, always 0 or positive. So one disadvantage for that is like if you have a node that just going through this new one, then you expect that like all this output from this node will be positive, right? So when it gets to the next computational node, or like next new one, it will be all positive values. So think of like you have the next computational nodes is like this. It's, let's say it's just you're computing again like a summation of a weighted sum of all your input plus a bias, and going through a function, some kind of another activation function. Now if I compute the gradient or compute the partial derivative of this guy with respect to the parameter, because you want to change the parameter, right? If I compute with respect to some wi here, wj, let's say, what I have will be just simply partial f, partial this thing, right? This thing is, let's say I just call it O, multiplied by, let's call this O, partial O, partial wj, right? And partial O, partial wj is just equal to xj, right? And as I just mentioned earlier, all this xj here are coming out from another new one, coming out from the sigmoid function there, and all of them will be positive. So therefore, like all these values are basically positive or equal to 0. Anyways, like bigger than equal to 0. And this guy can be positive or negative. But in any case, therefore you have a gradient will be either all positive or all negative, right? You cannot have a mixed values. You basically have a vector. It will be either all positive or all negative. So a disadvantage is like if you have a, let's say just look at, assume your vector is just 2D, it's like 2 dimensions in a 2D space, then what happens is like because your gradient is either all positive or all negative, it can only go either let's see, it either like here or here. If it's here, then if it want to go down here will be like opposite of this guy, will be like this direction, right? If it's here, it's a little bit ugly. If it's here, if I want to go down here, will be opposite of this guy, will go this direction. So anyway, like you will be restricting. Let's see. I made another mistake here. I need to be very careful. Otherwise, I will have another correction next time. So again, like you can have either like gradient here or here. If you have a gradient here, let's say, then you go down here, you have a direction here, right? So if I want to find the minimum, I need to go down here. So I will go to this direction here. If I have, let's say I have a function here, I mean the gradient is here, then I go down here will be in this direction here. Actually, this plot is bad, but it doesn't matter. So therefore, like what I have is like I will restrict my my derivative can only go into like this. Essentially, it's this direction and this direction. So therefore, it can only go through some zigzag path. Actually, actually, this is okay. This is not really bad. This is actually okay. So I can only go like this way or this way. What I mean is that I cannot go straight this way. The maximum I can go is here, but I cannot go this way. You see that? So therefore, like when we do the optimum, we are forced to go through some zigzag path, basically. This, something like that. So it won't be as efficient as if our gradient is allowed to be like have both a positive and negative element. Of course, if you look at that in just 2 dimensions, it doesn't look too bad. But imagine that if you go to high dimensions, for example, even for 3 dimensions, you have like, this is like 4 quadrant, right, in 2 dimensions. in 3 dimensions, you have 8. I don't know the English word for that option, or like I don't know how you, but then like you will restrict to like only 1/4 of all the space. And if you go even higher dimension, it's even worse. You restrict to 1/16 of all the dimension, all the space possible. So therefore, like it's actually, you see, like if you have a really high dimension, you get pretty significant this side effect. So therefore, it's not something you really want. And the third thing is that it's actually, I think it's a minor comment. Exponential is a little bit computationally intensive. I'm not exactly sure about that, because you can draw from a table and maybe you don't need to compute it exactly. But I think like, this one is very significant. Yeah. And probably this one has a lot of effect also. So let's look at some other alternative. Let's say I can use tanh. So tanh is very similar to your sigmoid function, right? You essentially just shift the mean to 0, and then you at least you get rid of the effects that like now you have 0 mean, so your derivative can have element both positive and negative is much better when you train it. But still, like you will have saturated region. Yeah. So if you have many levels, still there potential that like you're not able to propagate back any gradient information. So to take care of that, like people introduce a ReLU. It's like rectified linear unit. It's essentially it's also like last time in another context, I guess we call this a hinge function. So if you basically, because you have a shape like this, here you won't have any kind of problem with gradient saturation, right? So you will always have some gradient going back. That's one very positive thing. Of course, still like it's not zero center, so it will, if you kind of train it, it will still basically the training path will still go for a zigzag path. So but still like this is very common. Actually, ReLU is very common, very commonly used. And of course, like when you have x less than 0, here you also have saturation also. So therefore, if you think of that, if you go really for a very deep network, eventually, your derivative information will also like kind of get kicked out, like cannot propagate all the way to the end, to the beginning. But it would be better than like sigmoid and tanh, because you think of like only half of them is gone. But for that one, you can have like much more portion will be gone, because saturation is much more common than you expected.
Can I have a question, please?
Yes.
When you say it's better, is it in general better, or in some functions, in some applications?
Actually, I think it's like quite generally better. Nowadays, like many people will simply start with ReLU. Yeah. When they build a neural network, they will just start with ReLU instead of like starting with like tanh, for example. So therefore, as a rule of thumb, you may also like just start with ReLU and see like if your network is doing well. If not, you can try other combination. But you may not even need to go back to tanh, for example, because there's other possibility I will mention here also. It's like some other refinement of ReLU. And also, like for ReLU, there's a slight annoyance there, is because you have the cutoff is like exactly here, right? So if you initialize, kind of like if your input, when you initialize the network, because you need to initialize the input somehow, you need to initialize the network. if you initialize in such a way that when you start with your input is already less than 0, or like when you sum it up is already less than 0, then your node there will become stuck. It's not going to change. Yeah, I'm thinking about that. Is that a valid statement there? Let's see. At least like this is some people believe, honestly, and that's why like some people what they did is when they initialize that they will slightly bias the input. That basically this here, right? Because your let's see if I have. Okay, when you have the new one, you also when you do the weighted sum for your input, you always add a bias there, right? And you add the bias and go through the activation function. Let's say you go through the ReLU. So what some people did is like assume your input is more or less 0 mean, right? Then this guy is close to 0. Then what they did is like they also add a small, slightly positive bias here, just to make sure that like the new one doesn't start with 0 there. If you start with 0 there, basically again like, you cannot pass back any information for that particular value node. That's what some people did. But honestly, it's not hard to say whether it's making really the improvement or not. Some of these things, I guess people can still write a paper on that and do some analysis and argue back and forth and so on. But at least there's some people will do that. And other possibilities like having this so-called leaky value. So in that case, we allow that the other side is not equal to 0 exactly, have not a 0 slope, but have a slightly positive slope. For example, I can have instead of max 0 and x, I have max 0.01 x and x. So in that case, it will be, okay, it's kind of nice. Now it won't be saturated, and it's quite computationally efficient also. And most importantly, you can always pass through some kind of information. So therefore, to answer your question like earlier, so maybe if you start with value, it's not doing well, you can try, for example, this liquid value, or even this parametric rectifier value, or I don't know how to pronounce it, P value, something like that. And basically, this one will be very similar to this liquid value, just like you have this 0.01, you will make it as a parameter also, you make it as an alpha. So if you think of as a parameter, you will try to compute the derivative also, and you can try to train the model, like train this alpha as well. And of course, you will just get more and more parameter also doing this. And there's another variation is like E-loop, I don't know, just many loop. And so it will be very much similar to this previous one, but you will have this side is basically have this a little bit exponential decay rather than like it's like linear going down. So I don't know whether it's really much better or what, but one thing is like using this you can tune, because like for this previous one, the liquid value apparently is not 0 mean. So, but for this guy, you can tune this alpha such that to make it 0 mean, right? So, yeah, there's a trade-off here. So, of course, if you use this guy here, now you have some saturated region. So, whether you want to have some saturated region or you want to have 0 mean, then you just need to get I don't know. You need to decide yourself, basically. So we can go even a little bit more complicated. Let's say we have this mass function of these two, right? So we can go pretty general. Let's say you have max of like these two different function here, linear function here. But then in that case, if you pick this choice, you have much more parameters. So you just double the amount of parameters. So the pose, as I mentioned here, like apparently it's linear, does not saturate, will not die, and so on. But then you really double the amount of parameters. So so in practice, like you may just start trying to use ReLU, and then and see and be careful with your learning rate. See how we'll talk a little bit more later on. So the learning rate is just, if you remember, you have the gradient, you want to go down, right? So you have the parameter is equal to the updated parameter will be equal to your previous parameter added for the most simplest case. We'll subtract your gradient multiplied by your learning rate. So you can tune your learning rate somehow to decide whether you want to learn faster, but in that case maybe less computationally stable, or you want to just reduce the rate and so on. So and then and when you try ReLU, it doesn't go well, you may try the other things like liquid ReLU and so on. You may also try 10H, but don't expect much, and basically that doesn't make too much sense to use sigmoid anymore. So you can always ignore sigmoid. So that's comment for activation functions. Any questions? I guess it's pretty simple stuff, and I guess the guy who asked questions is now gone. I assume no questions, then I will just move on. Okay, I will talk a little bit about preprocessing. Really quick, just a quick remark, maybe less than 5 minutes. So, before neural network, before deep learning, people typically will do lots of preprocessing for your input data. We still do a little bit preprocessing. Basically, the key preprocessing we will do is we will typically do a zero mean for your data. Because remember, just we showed earlier, if your input is all kind of biased, all positive or all negative, then the gradient will be restricted into a very small space in the whole gradient space, I would say. Therefore, the training will be not quite effective. So therefore, you always want to just make sure you won't have input data is all positive or all negative. So one way to make sure that will be simply make it zero mean, right? So it's very easy. You just subtract the mean. You make the data will have zero center. Will be zero center. Sometimes you can also normalize the data a bit. You can maybe scale back. For example, here, this axis and this axis have different variance. Maybe we can kind of scale this by divide by this standard deviation, and divide this dimension by this standard deviation, and so on. People can even do decorrelation and also whitening. So when you have data correlated, then basically if you think of you have a bunch of data like this in high dimension, when you have correlated data, essentially your data cloud will not be aligned, will not align with your X and Y axis or Z axis, whatever axis. When your data get decorrelated, you will have the whole data cloud will be aligned with all the axes. And then afterward, you can do whitening and scale back. But typically, these steps are not quite common when you work on neural network. They are usually not needed. So, therefore, in practice, when you work on neural network, typically you only need to center the data. So make it zero mean. For example, if you look at different example work in recent years, for example, AliceNet what they did, they just simply do the mean image. So they subtract the mean, and I'm also VGGNet, also like another kind of like CNN kind of stuff. We'll talk more about that later on. Also just like subtract the per channel mean. They do not do any like normalization and PCA whitening and so on. Okay. Next, what I want to talk about is a pretty important topic. Is weight initialization. Actually, this is also one of the main reasons people cannot achieve like deep learning in the past, because until very recently, people initialize the weight rather arbitrarily. Because it's quite natural, right? You have the whole little network. You have many weights here, and you need to initialize them somehow, right? And one natural thing you can imagine. Okay, how you are going to initialize the weight? The first thing, what you will do? Like what? If you first, like, if you don't know anything, you now have a network, now you just want to initialize the weight somehow, like, what will you do? Yeah, small size, but, so I guess you want to say randomly, something like, pick it randomly, let's say. Definitely, if you pick it all zero, it'll be really bad. You will have nothing going out. So you need to initialize something. You cannot set it all zero. You may not want to make it like deterministic. Also, you may not want to set all the weights to be like some A, B, C, D, or like 1, 2, 3, 4, or something like that. Or 1, 2, 3, 4, you can make it random also, but you probably don't want to make it like all 1, for example. So the first very intuitive things people will do is, okay, I'll just set all the weights randomly. So I for example, like, kind of just drawn the weight from a Gaussian distribution, like take a random Gaussian, zero random number, something like that. But the problem for that, as people now realize, is actually it's okay, kind of okay for small networks, but actually it won't work when you have many layers. Because I'll just give a very simple example here. Let's say I have a 10-layer network here, so you can ignore the code here. Let's say 10-layer networks, and each layer have like 500 neurons. And let's say I use 10H for nonlinearity, as discussed earlier. So if I just initialize the weight randomly, and let's say we want to see like what we will have for the mean values of all the output after each layer. Let me articulate better. What's the mean output at each layer? So this is just plotting the mean output at each layer. So of course, I'm sorry, it's not exactly mean output, the distribution of the output at each layer. So, and yeah, this really look like to me is just, so, and what you can see is like in the early layer you have some distribution, right? But when you continue to go down there, you basically, everything just goes to zero here. So you have a peak at zero. So you basically doesn't have anything. So if you doesn't have anything, of course you cannot train this network, right? Because you just have zero here, then when you, that's basically when you compute the, yeah, I guess it's kind of apparent enough. If you have zero there, there's no information there, right? How can you train this network here? So of course, you can say, okay, maybe my weight is too small. Then one thing I can do, maybe I scale it up a little bit. But then if I scale it up a little bit, then I'll just go to the other opposite. So every layer, I will just get saturated. So the output will be either 1 or -1. And you remember that if you are in the saturated region, again, you cannot change it because then the local derivative will be all 0. So when you backpropagate a derivative, you're just backpropagating 0. So the problem here is like people didn't think carefully like what they should kind of assign the variance of the weight. Actually, it's okay to assign the weight from a Gaussian distribution, but the problem is like it's really sensitive to the variance of the weight, variance of the distribution. So actually the goal here is very simple. It's amazing. Like if you're like 4 or 5 years back, if you think of this, and you can write a very nice paper like just here, this couple 9 of equation, and you can really have like, of course, like the paper like beside this they have simulation and so on, but this is one of the very important things they bring out. So what they want is like, let's say, start with something simple. Let's assume we don't have an activation function here. So let's say I just have like some inputs coming in, so some x1, x2, and so on. And I weighted that, so and they sum together and have a weighted sum weighted by wi here, and then I have a y here, and I have this activation function here. It's just an additive function, so I have nothing here. So maybe y here, so I don't have activation function here for now. So what we want is like we want to have like the input going for each layer basically still have the same energy, or like still have the same variance. We don't have the variance to change. So let's compute the variance of the output. The variance of y will be just equal to the weighted sum, right? Variance of this weighted sum. And because variance is basically a linear operation, kind of. Not, okay, I need to be really careful. It's not actually linear. But for the variance operation, I have variance x plus y is equal to variance x plus variance y. So my variance operation can get into the sum. Now this guy, do you know what is that? Actually, I would be quite impressed if you know what is this, how to compute this guy. So this is a random variable, this is a random variable, and I can give you an additional assumption that like these two, let's say they are independent. This random is reasonable. The weight, supposing it should not depend on your inputs, or at least at the beginning, right? So how do you go ahead to simplify this equation somehow? So it turns out that it will be equal to this, something like this. I mean, this variance, this guy is equal to this. It's not hard to show. It will be like a slide of algebra, but you will need a little bit knowledge of like expectation and variance and so on. So remember that like, okay, let's say I have a variance of x and y. Remember this equation? I'm not sure that you guys, so you should have learned that like in some probability or statistics class. If not, is remember like what is variance is originally defined. It's like variance of, let's say W is equal to expectation of W from its mean, right? And the square of that, right? So it's basically measure like the square difference of each of the variable from its mean. So if this guy, if I kind of expand this, I will have like W square minus 2 expression W expectation W square, and then expectation operation is linear, I can get into each of the sum as have expectation W square minus expectation 2 expectation W plus expectation of W square. And of course, like when you do an expectation, you're computing the mean, right? Once you compute the mean, this thing is a constant, right? So the expectation of expectation is just itself. So the expectation of expectation is just this. And this, therefore, like this guy is a constant. 2 expectation W is constant. You can pull it out. And then you have, therefore, you have 2 expectation W, expectation of W. So this guy will give you 2 expectation W square. So these two guys cancel one of them. Therefore, you have this way. You have expectation W square minus expectation W square. Yeah, this is an important equation. So if I think like all engineers should know this. Yeah, when you, yeah. So, then okay. Then we can use some assumption. Then like next step we need some assumption. We need to assume that like X and Y are uncorrelated. If you want to get stronger, you can assume they're independent. If things are independent, they will be uncorrelated. But the property of uncorrelation will be like when you say X and Y are uncorrelated, expectation X is XY will be equal to expectation X multiplied expectation Y. And because X and Y are uncorrelated, you expect the square values will be uncorrelated also. It will be something like when you say this thing and this thing are independent, function of this guy should still be independent of function of this other guy, right? This is lateral, right? So therefore, like, I will have this is equal to this guy here, and I have also like expectation xy is equal to expectation x, expectation y. On the other hand, if I compute like variance of x multiplied variance of y, I have this, and then this is a little bit hard to read, so you need to be very careful. Like you have this is expectation x squared, but this is expectation x and then square. Then you compare these two terms here, so I can pull out, I want this guy from here, so, and I need, and then like I can have this guy weighted as like, I can add one more terms here to have this here, because if I add one terms here, this guy, I know this is equal to variance of y, right? That's what I want from the result. And then similarly, I have this here. But since I add this term and add this term, I need to subtract back these terms, right? I need to subtract back 2 expectation x square and expectation y square. And if I add this, then I have 1 minus 1 expectation x square and expectation y square. And then I know this, okay, this is variance of x, variance of y, so therefore I have this is equal to that. So that's exactly what we have here. So variance of xy is equal to this guy here. So any question? So then what next? Then we can do another assumption here. So assume that like our input and also the weight initially is zero mean. So then I will just assume this will be equal to 0. So I only have one term left. I only have this left. And then variance are actually just some statistics of a distribution, right? Therefore themselves is constant. So I shouldn't say that. I should really say like I will assume that for each of this input and output, the statistics are the same, so therefore like variance of xi are all equal to variance of x and variance of wi are all equal to variance of w. So therefore I have n of them, I have n multiplied by that. Now I have this variance of y is equal to this multiplied by this. Now if I want to make sure the input variance or the output variance is the same as the input variance, I should really set this to 1, right? So therefore, I should enforce that the variance of your weight should all equal to 1 over n. And if you try that, actually it looks pretty nice. That's the case, like, okay, actually this is also called Savia initialization. So it's really simple, right? If you look at that, it's really just a random, also initialize the weight randomly, but you adjust the variance very carefully. The variance should be equal to 1 over the number of input to this node, to that particular node. But remember that, like what we just did here, we assume that the activation function is just an identity function. I'm doing with time. So in terms of ReLU, there's and I don't have the citation here. Also, this paper is pretty recent. I think it's 2015. So again, it's like some very simple analysis, but it's a nice paper. Of course, they have other things also again. So if I have a ReLU, then my previous analysis won't be correct, right? Now let's say okay, remember that what we mean by ReLU is like I have x coming in, I have some weighted sum here, have weight w, and then I will then go for this ReLU function. It's like the hinge function that I have a y here. So when it's bigger than 0, it's just equal to the input. When it's less than 0, it's equal to 0. And so now let's denote YL here is the variable considered as a variable at the L level. So the output at the L level, and XL is the wait a second, it should be simple. Okay, I'm sorry. Actually, Y is here. Y is here. Y is assume Y is the notation. YL is the output before going through the ReLU activation function. So this is YL XL here. Now, therefore, the variance of YL is just the weighted sum for XL. Then we can go for exactly the same step, right? It's equal to this here. But now we need to be careful. Like we have different assumption here. We can still press the wrong button. We can still assume W to be 0 mean, but in general we cannot assume X to be 0 mean. Here we can see the picture, but okay, because X is just going through an activation function, right? Going through the ReLU function. So anything go through the ReLU must be positive. Apparently, it's not 0 mean, right? So therefore, like this term here, I cannot assume to be 0. The mean cannot be 0. So therefore, instead of like previously, the previous analysis and 3 terms, I have 2 terms here. 2 terms left, and then like here, I was confused by this step, like last slide for 5 minutes. I wrote this slide like last year. I thought that there was a bug here. Just the notation is not super clear, so you can see like this square is inside here. So this is basically, remember again, like variance is equal to expectation XL square inside minus expectation XL outside. So therefore this got cancelled. Therefore, I mean this term and this term got cancelled. So I only have this term left. So, and what can we say about expectation XL? It should leave this. The unfortunate thing is that every time I draw this, the picture is gone. Let's see. Again, I have X here, have Y here, and have the activation function here. So this is XL. I have an activation function going through here. So therefore, like this is YL, right? This is XL, and I have this is basically have a YL minus 1, right? Yes. And this is a weighted sum here is XL minus 1. So what can we say about like XL, the expectation XL square, and the expectation YL square, or like the variance of YL square? Actually, what can we say about like expectation XL square and expectation YL square? Can you write the equation for that? Can you link this with this somehow? More than that, right? This function here, remember, is just a value. So when it's bigger than 0, it's equal to the original value. When smaller than 0, it's cut off to 0, right? So if this guy here, let's see, so therefore, like, we can, okay, this may be an approximation, but essentially what we have is like approximately half of the time it will be keeping itself, half of the time it will just equal to 0, right? So therefore, like, if you think of this as like the energy, right, the mean of this square value, so you cut off half of the energy, right? So that should be like half of the original. And I am thinking this is a jump of step. Variance of YL is equal to the expectation of YL. Why is that? Is that correct or not? Let's see. Why is I'm not completely convinced, but I guess if it's approximation, it's fine. So this is approximate the energy also, like before the value function, and this is the energy after the value function. So you cut down like half the energy, so there will be half of that. So, but anyway, like this, I guess that should have some kind of approximation. Then maybe I'm kind of happy with that, like for this moment. So therefore, we arrange that. We have this thing again. So again, like the key is that we want to have the basically the energy going through the layer doesn't change, right? So therefore, like when it going after going through this layer, I will have like the energy will be go up by this value. So therefore, I want to make sure this value is equal to 1. So if this value is equal to 1, then it means that my variance should be like 2 over n. So compared with like what we have previously, I have 1 over n, but this guy also have 2 over n. And actually, if you do it experimentally, it works quite well. So this is with this initialization. Okay, the paper is 2015. So just add 1/2 to the Xavier initialization. But now, if you have this value activation step, then you after like 10 layers, you still have like reasonable amount of energy here. So you don't, I mean, everything got saturated or like, it won't get 0 like everywhere. So any questions? Let's see what's this slide here. Oh, yes. Yes.
Why do they want to conserve the variance of y not enlarge it.
No, they don't want to enlarge it because you will explode. It's like.
But I think the larger the better.
No, okay. First of all, like it always won't be larger. But it's always I can ignore the theory because theoretically I'm not sure it's larger or better or not if every step is valued. But there's a couple consideration here. First of all, like your computer have finite precision. It's not larger is better because eventually if your value explode, you have this RGB whatever standard, right? The precision it cannot store that values. Secondly, like it doesn't necessarily like all the layers only have this value activation function. So maybe you have some of the layer is actually maybe you still have some sigmoid or like you have some 10H there. Then in that case, like your values, if it is too big, it will get saturated again. So if it gets saturated, then you cannot propagate back your derivative.
But maybe we can multiply it by a small factor, and maybe we can get a better formula.
But how? Okay, maybe.
For example, we can get the double times y, the variance.
So I'm not sure I get your question precisely. So if you say like you multiply it by small values or something like after you multiply by w, you just make the values of w changes, right? You're just basically scaling all the values of w, right? Is that what you mean?
Oh, I see.
Yeah. So, any other questions? So, what are we doing time? We have like 10 minutes. So, overall weight initialization is, I'm not sure it's an active research area. So I checked this CS231N, like last year they say it's active area, this year they also say active area. I think they have the same slide though for this particular part. But I guess like, yeah, if you're interested, I guess you can still do something, for example, because you can think of like you have different activation function. We only show valued, let's say. I'm not sure that maybe they have other works. Apparently they must have, like, let's say if you want to deal with the other variants of like loop, like you have this parameterized like loop, that one I guess you cannot do anything about that, but you have this U loop also. Maybe you want to see like how you can initialize the weight properly for let's say E loop, like let's say, right? And apparently, if you change the activation function, you need to do something differently from you do to do the weight initialization kind of wisely. And so I guess I probably stop here because I don't want to start something new. So, any questions? Besides that, you guys are good with homework, like, yes?
Oh, I have a question
Yes.
about the AKII function. Why the slope as a negative part is much smaller than the slope as the positive part?
The liquid value, right? Actually, I guess it's just a preference. It's like more like a convention. I'm sure that you can do the opposite. You don't want to do the same, right? Your slope cannot be the same, then you will get identity function. Yeah.
But if it's identity function, it would be much simpler. The we can drop out this.
Okay. Remember, like, we always need to have some nonlinearity in your neural network. Otherwise, like, if you don't have any activation function there, you don't have any nonlinearity there, then there's no point you have like multiple layers, because what you're going to do is you just keep on multiplying some matrices, right? You have like W1 multiply W2 multiplied by W1 is the same as like just think of it one big matrices, right? You won't have any benefit like to have multiple layers.